All right, today we're going to pull back the curtain on the hidden world of chemistry. We're going to uncover the 3 secret rules that basically decide if a chemical reaction is a go or a no-go. Okay, so get this. Inside just one tiny cubic centimeter of air, that's like the size of a sugar cube, molecules are crashing into each other an insane number of times. We're talking 10 to the power of 33 collisions every single second. That number is it's mind-bogglingly huge. So with all that constant smashing and bumping, you gotta wonder, why isn't everything just constantly exploding or changing? What's stopping it? Well, it turns out that most of the time, it's nothing. It's just a harmless little bounce. The particles just kind of hang off each other and go on their merry way, completely unchanged, especially when things are a bit colder. You get tons of collisions, sure, but they don't actually do anything. So, yeah, it's pretty clear that just bumping into another molecule isn't the whole story. So, to really get why, we need a way to think about all this, a framework. And lucky for us, there is one. It's called collision theory, and it's what gives us those 3 secret rules we're looking for. And collision theory kicks off with a really simple, almost obvious idea. For any reaction to happen, the particles they have to collide. They have to physically touch. No exceptions. It's rule number 1, the absolute, non-negotiable first step. You know, a great way to think about this is with cars. Imagine you're parking and you gently tap the bumper of the car behind you. It's a collision, technically, but nothing really happens, right? No scratch, no dent. But a high-speed crash on the freeway? Whoa. That's a totally different story. That's a massive, chaotic rearrangement of parts. It's the exact same deal with molecules. Not all collisions are created equal. Okay, so that brings us officially to rule number 1. It's the most basic one. You must collide. Simple as that. Before anything else can even possibly happen, the reactant particles have got to physically smash into one another. So logically, if we want to speed up a reaction, what do? We just need more collisions to happen more often. And the easiest way to do that? Increase the concentration. You just cram more particles into the same amount of space. It's just like being in a super crowded room versus an empty one. You're way, way more likely to bump into someone. More particles means more collisions, and that means a faster reaction. And this is where we need to make a really important distinction. There are 2 types of collisions. You've got your ineffective collisions. Those are the harmless little bounces we talked about, but then you have effective collisions, and these are the ones we care about. These are the high-speed, demolition derby crashes that have enough oomph to actually break old bonds and let new ones form. That's what makes a product. So really, the whole game of chemistry is trying to get as many of these effective collisions as possible. But just like with our car analogy, just hitting each other isn't enough, right? A gentle tap does nothing. Which brings us right to rule number 2. You have to hit hard enough. The collision has to have some real force behind it. I mean, it makes sense when you think about it. Chemical bonds are strong. They're like a super strong glue holding atoms together in a molecule. If you want to break that glue, you can't just gently tap it. You've got to smack it with some real energy. You need a powerful, forceful impact to shatter those existing bonds and get the whole reaction started. And this minimum amount of energy needed, well, it has a name. It's called the activation energy. A really good way to picture it is like a big hill. The colliding molecules are trying to get over this hill. If they don't have enough speed, enough energy, they just roll right back down and nothing changes. But if they hit the hill with enough force, they make it over the top, and bam, the reaction can happen on the other side. So you might be wondering, just how high is this energy hill? Well, for some reactions, it's massive. Take the Haber process, for example. It's super important for making fertilizer. At room temperature, only 1 out of every 100 billion collisions actually has enough energy to make it over the hill. 1 in 100 billion. That just shows you how incredibly rare a successful energetic collision can actually be. So what's the trick? How do we give more of these molecules the energy they need to get over that barrier? It's simple. We turn up the heat. When you increase the temperature, you're basically making all the molecules move faster. They're zipping around like crazy. And that does 2 things. 1, they collide more often. But 2, and this is the important part, their collisions are way more powerful. So at higher temperatures, a much bigger chunk of those collisions will have enough energy to clear that activation barrier. You get more useful collisions, and the reaction just goes faster. Okay, so let's recap. We've got our first 2 rules down. You have to collide, and you have to collide with enough energy. But there is one more piece to this puzzle, a final secret ingredient. It turns out, even if you have a collision with tons of energy, it still might not work. The collision itself has to be, well, perfect. And this brings us to rule number 3, the perfect angle, or what chemists call orientation. Think about it like this. Even if two molecules slam into each other with incredible force, if they don't line up in exactly the right way, poof, nothing happens. The specific reactive parts of each molecule have to be the parts that actually make contact. Just take a look at this. On one side, you have a fruitful collision. See how they line up just right? It's perfect. That allows the old bonds to break and the new ones to form. But then look at the unfruitful collision. They hit each other kind of side on, all wrong. Even with all the energy in the world, the wrong parts are touching, so they just bounce off each other. No reaction. Let me give you a concrete example. When hydrogen chloride tries to react with ethene, it only works one way. The hydrogen end of the HCl molecule has to be aimed directly at that carbon-carbon double bond in the ethene. If it hits any other way, say with the chlorine end first, nope. The negative charges just repel each other, like trying to push two same-sided magnets together. They just bounce apart. The angle is literally everything. All right, there you have it, the 3 secret rules. 1, you must collide. 2, you must collide with enough energy. And 3, you must collide at the perfect angle. So now that we know the rules, here comes the fun part, we can start using them to take control. You see, the real power of this theory isn't just about understanding what's happening, it's about manipulating it. Once you know the rules of the game, you can start to bend them to your will. We can now intentionally make reactions go faster, or even slow them down to get exactly what we want. And here's our toolkit. How do we do it? Well, if we want to tackle rule number 2 and get more energy, we just increase the temperature. Simple. If we want to tackle rule number 1 and get more collisions, we increase the concentration. For solids, we can increase the surface area. Think about how much faster dust burns than a log. That's exposing more particles for collision. Or we can cheat a little and use a catalyst. A catalyst is like a chemical matchmaker that lowers that big energy hill, making rule number 2 way easier to achieve. So this really brings it all together, right? An effective collision, the only kind that actually matters, is this incredibly rare, perfect storm. It's that one moment where the particles collide. They hit with enough energy to get over the hill, and they're lined up in the perfect orientation. It has to be all 3, all at the same time. So what this all really means is that chemistry isn't some kind of random magic. It's really just a game of odds, a game of probability. And it's all governed by these 3 surprisingly simple rules. And now that you know them, start looking around in your daily life. I mean, when you put leftovers in the fridge, what are you doing? You're lowering the temperature to slow down the chemical reactions that make food spoil. You're manipulating rule number 2. When you use hot water to get a tough stain out, you're speeding up a reaction. So the question for you is, now that you know the rules, where else can you see them at play?